All right, so once again, you might want your graphing calculators for today's lesson. We're going to be hitting up lesson 5.5 today, and it's going to be pretty similar to what we did last time. Honestly, there won't be a whole lot of new stuff, just a different question, but using the same skills, basically. So what we're going to be doing is we're finding intervals of increase and intervals of decrease of a given function. And what an interval of increase is basically just where the graph is going in a downward direction. And an interval of increase is where it's moving in an upward direction. And that corresponds to the fact that a function is increasing when its derivative is positive. You don't need to write this on this example, but you might want to write this somewhere on your notes. So if f prime is positive, then f is increasing, which we talked about that last time anyway. And if f prime is less than 0, in other words, it's negative, then f is decreasing. And that's what we're going to be looking at today. Now, we could do all these problems with a calculator, but I want to make sure you guys know how to do them by hand, but we'll also do it on a calculator just so you guys can kind of see all the varieties of ways that the questions can be solved. So let's go ahead and start by doing it by hand first. So it's asking us to find the intervals where the function is increasing and the intervals where the function is decreasing. So the first thing we're going to do is we're going to find f prime. So the derivative of this is 12x cubed minus 6x squared minus 90x. All right, once again, we're going to go ahead and find our critical values. So I want to find out where f prime of x equals 0. I also want to find where it's undefined. Now, this is a polynomial, so there's not going to be anywhere where this particular derivative is undefined. But we can find where it equals 0, so let's set that equal to 0. And we're going to go ahead and solve it. So I like factoring, so I'm going to go ahead and start with that. Let's see, 6. I think 6 goes into all of these and x. So I'm going to see if I can divide out a 6x here first, a greatest common factor. All right, and then I would factor this using the box method. And for those of you guys that need a little bit of a review on how to do the box method, I can take some time to do that really quick. So what we do is we put the first term here, 2x squared. We put the last term here, which is negative 15. We ask ourselves what times what makes 2x squared, and that would have to be 2x and x. And what times what makes negative 15, that would have to be 5 and 3. One of them has to be negative. Now, you could do this next part mentally, because at this point what you want to do is you want to check to make sure it works. And here's how you know it works. 2x times 5 is 10, and 3 times x is 3. Now, what we need to have happen is that somehow these two terms need to be able to add or subtract together to make x, and they don't. They should add up to make that middle number. So that means we have a problem, and what you want to do whenever it doesn't work out the first time is you want to switch the numbers. So I'm going to put the 5 down here, and I'm going to put the 3 here instead. So now let's try it. So that would give me 6x, and this would give me 5x. And those can combine together to make that middle number there, negative 1x. If the 6 is the negative, in order for that to happen, the 3 would have to be negative. And so you could double check it here, but 2x times x makes 2x squared, 2x times negative 3 makes negative 6x, 5 times x makes 5x, and 5 times negative 3 makes negative 15. And then these, the crowning moment, comes whenever those two terms add up to make the middle. So that means that this polynomial factors into 2x plus 5 and x minus 3. All right. So setting these three factors equal to 0, if I set this one equal to 0 and solve, I would end up with 0. If I set this one equal to 0 and solve, I would end up with negative 5 halves. And if I set this one equal to 0 and solve, I'm going to end up with 3. So we end up with 3 critical values that we're going to need in order to find the intervals of increase and decrease. So the next thing we're going to do is we're going to do our number line. You guys are noticing this is almost exactly like what we did yesterday, right? There will be some minor differences at the end, but for the most part it's really quite similar. So putting these critical values in order from least to greatest, we have those things. And it breaks it up for us into 4 intervals. And once again, we're going to take our derivative, and we're going to plug into our derivative a test number from each interval. Okay, so I'm going to plug in, this is about negative 2.5, so I'm just going to plug in negative 3. Here I'm going to plug in negative 1, positive 1, and 4. All right, we're going to plug those into our derivative. I'm going to be using a calculator to see what I get. So let me pause my video here, and when I unpause it, you will see my solution. So these are the values I get. So we have a negative slope on the first interval, so it's going in a downward direction. And then we have a positive slope on the next interval, followed by a negative slope, followed by a positive slope. Now, at this point, you could identify your relative max and relative min, but they're not really asking us to do that in this particular case. They just want to know what are the intervals of increase and what are the intervals of decrease. So these intervals from here to here are the ones where the graph is going in an upward direction. So that would be this interval here from negative 5 halves to 0, and this interval here from 3 up to infinity. So f is increasing on the following intervals. Negative 5 over 2 to 0, and 3 to infinity. Okay? Now let's do the next one. Let's find where f is decreasing. Well, it would be the other ones, right? So we're decreasing here and we're decreasing here. So that's this interval, and this interval is where we are decreasing. So that would be from negative infinity up to negative 5 halves, and from 0 to 3. Okay? And so that's our answer there. So the only part that's really different is at the very end. Instead of stating what the relative extrema are, we just talk about which intervals are the intervals where the function is increasing and which intervals are the intervals where it's decreasing. All right? All pretty much the same stuff. All right. The only thing you'll notice that was really different in the other steps was at the beginning, I didn't bother checking for continuity. You don't really need to do that because we're not looking for a specific point anymore. We're just looking for intervals of increase and decrease. So you're going to use any and all critical values you could possibly find, even the ones that are points where it's undefined. All right, so here's a student practice for you guys. Go ahead and pause the video and solve this problem. When you unpause it, you will see the solution. All right, so here's the solution. I'll let you guys study it a little bit there. It looks like it's increasing on the left-hand side and on the right-hand side. And the other two intervals, which are the ones in the middle here, it's decreasing. So decreasing is here, increasing is here. Now, some people might ask, well, since these two are together and they're both decreasing, Can't we just say it's from 0 to 4? And I would say no. And the reason for that is because it's not decreasing at 3 over 2. At 3 over 2, the derivative equals 0. That's where that came from, right? So at 3 over 2, the function is not decreasing. It's 0. So I would guess that this graph would probably look something like this. It's going up, and then it starts to go down. Then it gets flat for a split second at that point, and then it starts to go down again, and then back up. So we have a 0 slope there, but it's not a relative extrema because the slope didn't change. It went from negative to negative. Whereas on these other two intervals, which actually, let me draw this a little bit better. So the graph is going up starting at infinity, right? And when it gets to 0, it starts to go down. And here, when it gets to here, it's 0, but it keeps going down after that. And then it's 0 again, and then it goes up. So this graph would look something like that, probably, if we were to put it on an actual piece of graph paper. Okay? But you don't need to know what the graph looks like. It's not horribly important, just as long as you can accurately identify the intervals. All right? All right, let's see what's next for us here. So I want you guys to consider this following graph, and for a minute I want you guys to ponder this. I want you to highlight the region in this graph where y is greater than 0. Highlight the region of this graph where y is greater than 0. Well, y is based on this vertical axis, right? Greater than 0 means positive. So all these points up here are places where y is positive. And all these points up here are places where y is positive. So I'll go ahead and highlight that in green. And so not surprisingly then, if I were to ask you guys to find me where y is less than 0, hopefully you guys would know that we would be looking at the places below the x-axis, right? And those places where y equals 0 are the places right where the graph touches the x-axis. So keep that in mind for now. So when you're looking at a graph, y is greater than 0 when it's above the x-axis, y is less than 0 when it's below, and y equals 0 when it touches the x-axis. So I'm going to introduce a new concept to you guys, the idea of the graph of a derivative. So suppose I have a function which I'm going to call y1, and that's f of x. Then we could find the derivative of that, f prime, and that's actually a whole different function. It's a whole new function in and of itself. So I'll call that y2. Now, since the derivative is itself a function, then we can graph the derivative of a function. And when you look at the graph of a derivative, anytime the derivative, f prime, is above the x-axis, that means f prime is greater than 0, which means that our original function must be increasing, because if its derivative is greater than 0, that means its slope is positive, which means that the original function must be increasing. In the same way, by looking at the graph of the derivative, if the derivative is below the x-axis, that means that the derivative is less than 0, which means that the original function must be decreasing on that interval. So, for example, suppose I gave you guys this function right here. Now, I don't want to graph this function. Instead, what I want to do is I want to find the derivative of that function and graph the derivative. So if we graph this function here, f prime, it would look like this. So I want you guys to understand something very important here. This graph is this function here. It is not the top one. So I've graphed this function, 6x squared minus 24, which is the derivative of this function on the top. Okay? So now, what's the significance of this? Well, let me ask you guys a question. Let me get my pen here. I need to write on my board. All right. Where is f prime of x, based on the graph, where is it above the x-axis? Where is f prime above the x-axis? You guys can see that would be here, and it would be here, right? So it's above the x-axis when f prime is greater than 0. And that happens on the interval that I've highlighted in green there. Now, on that interval where I've highlighted in green, if the derivative is greater than 0 on those intervals, then that means that the original function is increasing on those intervals. Okay? And those intervals are from negative infinity up to here, and also from here on up into positive infinity. So wherever the derivative is, if you're looking at the graph of a derivative, wherever that graph is above the x-axis, that means the derivative is greater than 0 there, which means that my original function must be increasing on that interval. Likewise, I could ask, where is f prime of x below the x-axis? Well, as you guys can see here, that would be happening down here. So in that case, my derivative is below the x-axis. And that means that on that purple area, f prime of x is less than 0, which means that on that purple area, that's where f of x is decreasing, because its derivative is less than 0, which means that the slope is negative. Okay? And that would be on the interval from -2 to +2, in between those two values. All right? So that is something that I'm front-loading for you guys to be aware of, because we're going to learn how to do the same thing that we just did earlier, which is finding the intervals of increase and the intervals of decrease. But I want to show you guys how to do it on a graphing calculator instead of doing it by hand. The benefit to that is, well, sometimes it can be a little bit difficult to solve some equations by hand, and so knowing how to do it on a graphing calculator can make things go a little bit smoother. So this time we're going to use a graphing calculator. So there's my function. Let's go ahead and see what we can do here. I want to show you guys how you can use a graphing calculator to make this a little bit easier. All right, so let's go ahead and get started here. Now, probably the best way to go about doing this one would be to find the derivative first. Now, for this, we're going to have to remember a couple of rules here. First of all, we have the product rule. I've got something being multiplied by something else. So we do A times B plus A times B, right? Where you take the derivative of one in one case and the derivative of the other in the other case. So if I fill this in, I would end up with 1 for the derivative of this A. I'm calling this A, and this is B. And then B, we're just going to put this here. And then A is x, and the derivative of a square root. Okay, so how do you find the derivative of square root? There's a couple ways, but there's a shortcut for finding derivative of square roots. You just do 1 over 2, and then you put that square root just the way it is, and then you multiply the top by the derivative of the inside. So the derivative of the inside is -2x. Okay, so there's my derivative, kind of a big, ugly, nasty looking thing. Now, if I were to simplify this x here, that's like x over 1, so you'd multiply the x to the top, and you would have -2x squared over 2 square root of 1 minus x squared. If you want, you can actually reduce these 2's away, and you can put the negative in the front. You don't have to do all that kind of stuff, but you can, because our calculator is going to do most of the work for us anyway. But If you want to just write it in maybe simplest form, it would look like this. Okay, so that's what we're going to be plugging into our calculator here. So here's my calculator. So we want to graph the derivative function that I just found. So we're going to press y equals. So we're going to push this y equals button here. And if you guys want to know what buttons I'm pushing as I go, you can follow along on the screen, but it also keeps a record down here, but I'll have to clear it every once in a while. So you push y equals, and then we're going to type our function in there. So the function that I had looked like this, and you guys can copy what I type in here. So this is what it should look like once you guys type it in. Now it's really important you guys understand you know, the difference between your negative button and your subtraction button. All of these are subtraction buttons. So anyway, we're going to graph our derivative now. So we can go ahead and press graph. And that's what my graph looks like. Now I'm going to zoom in a little bit. I don't like the way that this looks. You don't necessarily have to zoom in, but if you want to learn how to do that, you can do it now. Push zoom. Let's see. Let's do zoom in. There's a few different ways to zoom in. Push enter, and it zooms in a little bit more for you. So I pushed, once again, if you want to know those keys I pushed zoom, I pushed 2 for zoom in, and then I pushed enter. And that zooms in a whole lot. There's a lot of different ways to change your viewing window on here. Zoom is one way, window's another way. This happened to work out pretty good, so I'm going to stick with this. But anyway, so here's the graph of my derivative, right? Now, remember what we talked about on the last slide, on the last few slides. What we said was that anytime the derivative, which is this graph, is above the x-axis, that is an indication that f prime is greater than 0. And when f prime is greater than 0, that means that f, the original function, is increasing. And so on what interval is that happening? Well, we're not quite sure yet, but we'll get there. Okay? We'll get there. It's going from this spot to this spot. So we need to figure out what those two question marks are. And that's one of the things we're going to learn on our calculator today, but we'll get to that. Next, something else that we've already discussed is we also know that when it's below the x-axis, that's where the derivative is less than 0. So if f prime of x is below the x-axis, that means that f prime of x is less than 0, which means that f, the original function, is decreasing on those intervals because the slope is negative. Okay? Now, I don't want you guys to get confused when I say the slope is negative. I'm not talking about the slope of this line. Okay, the slope there is positive, right? But I'm not talking about the slope of that line. This is the graph of my derivative. And since the graph of my derivative is below the x-axis, that means that f prime, the derivative, is less than 0. And since the derivative is less than 0, and the derivative is the slope of f, that means that f is decreasing on that interval. The derivative is not decreasing, but f is decreasing. The derivative is below the x-axis, which means it's negative. All right. Now, here's the fun part. We've got to figure out what these 2 points are. Where is it touching the x-axis? So to do that, we're going to need to press some pretty specific keys to find that. Okay? So I'm going to clear my key history here, and you guys are going to want to follow along. So here's how you do it. The first thing you're going to do is you're going to push second. Then you're going to press the Trace Calc button. And you're going to click the option for number 2, where it says 0. Now, as soon as you do that, you're going to see a cursor blinking here, and you're going to see left bound. Let's say I wanted to find out what this 0 is right here, where it's touching that x-axis right there. I want to move my cursor to the left of that dot, so I'm going to slide it over. I unfortunately have to push the left arrow button a billion times. But now I've got my cursor to the left of that root, and then I'm going to go ahead and push enter. And that sets up like a barrier right there. Now it says right bound, so now I'm going to move my arrow to the right until my cursor is to the right of that dot as well. I'm going to push enter again. And what that does is it creates a barrier. And what these barriers do is we're telling our calculator, please look in between these two dotted lines to find where my graph touches the x-axis. The reason you have to do that is because it also touches the x-axis over here. So if you don't tell it where to look, it won't know where to look and it can't do it. So you have to pick a point to the left and a point to the right of the 0 that you want. Once you've done that, it says guess down here at the bottom, and all you have to do is push enter. And it will move your cursor right to the place where it needs to be. So that spot right there is negative 0.707. Negative 0.707. Now this graph looks really symmetrical. So my guess is this one's going to be the same thing. It's just going to be positive. But just for the heck of it, let's go ahead and do it again. So I want to find where it touches the x-axis over here. So the first thing we do is we push second, trace calc, 2 for 0, and then we're going to scroll until we are, you want to be to the left of your 0. I want to be to the left of that root. I want to be close to it, but I want to be to the left of it. Enter. And now I'm going to scroll until I get to the right of that root. Enter. And then I'm going to push enter one more time. And sure enough, it's the same number. It's just an opposite sign. It's not always going to be like that. Obviously, it depends on the function. But in this case, mine was symmetrical. So there we have it. So now that we've got all that fun stuff, let me bring back my notes here. We now can have our answer written for us. I now know that f prime of x, which is this graph that we're looking at, is above the x-axis. In other words, f prime of x is greater than 0 on the interval from negative 0.707 to positive 0.707. Now that means that that is also the interval where it's f, the original function, is increasing because its derivative is positive there. Now you'll notice also I chose to use parentheses and not brackets because those are the places where it actually touches the x-axis. And when you're touching the x-axis, the derivative is 0. And if the derivative is 0, that means that the function is not increasing at that point. It has to be greater than 0 to be increasing, right? So I use parentheses. Now, where is it decreasing? Well, we can assume it just kind of keeps going down on the left and right side. So from negative infinity all the way up to negative 0.707, it's decreasing. And also from positive 0.707 on the right off into infinity on the right. So there's your two possibilities there. So that's how you can use a graphing calculator to find your intervals of increase and intervals of decrease. Now, before we move on, I want to show you guys one more thing about this. We can kind of pull in the stuff that we've learned about in previous lessons. So notice here, I'm going from a negative derivative to a positive derivative. Now, when you're thinking about the original graph, the graph of f, if you're going, I'm going to make a separate graph for f. Remember, this is a graph of f prime, but I'm going to make another graph over here of f. I know that at this point right here, the slope goes from negative to positive, down to up, which means that this point right here must be a relative minimum value on the graph of f. It's not a relative minimum on this graph. On this is a graph of f prime. But this would be a relative minimum on the graph of f because it goes from, that's the point where it goes from a negative derivative to a positive derivative. In other words, a negative slope to a positive slope. Contrary-wise, this would be a relative max of f, because we're going from a positive slope, wrong color, a positive slope to the left of it, meaning it's going up on f, and going to a negative slope after it on f, which means it's going down. And so that would give me a relative max on the graph of f, right? But that's not stuff that we're talking about today. I'm just giving you a little preview of some stuff we're going to get to in some later lessons. For now, I just want you guys to know what to do here. So before I set you loose, we're going to go ahead and do a guided practice. So let's do another problem here, and this time we're going to do it kind of together, let you guys take it one piece at a time. All right, so the first thing I'd like you guys to do for this first guided practice problem is I'd like you to find the derivative, and that's something you're going to do by hand. So pause the video here and see if you guys can get the derivative. Okay, and there it is. So the derivative of sine is cosine, but we have a chain rule. So you have to multiply it by the derivative of the inside. The derivative of x over 3 is 1/3. The reason for that is because pen got goofy there for a second. The reason for that is because x over 3 is the same thing as 1/3 x, and when you take the derivative of that, you get what I have there. So there we have it. All right, so now what I'd like you guys to do is I'd like you to go ahead and get your graphing calculators out, and let's graph this thing. All right, so this is what I have here after having graphed it. If you want to see how to type it in, you should have had this. You want to put your 1/3 in parentheses. So if you didn't do that, your graph probably looks wrong. Also, you still might be in a zoomed in look. So if you want to get back to a normal look of your graph, like mine, what you're going to do is you're going to push zoom and then push 6 for standard. And that will make yours just look normal again. But once again, honestly, I don't really care. We could work with this. It's not that bad. I don't like how flat it looks. So what I would do is I like how wide it is because I can see it's below the x-axis, and then somewhere in here it crosses and then goes above, and then it crosses somewhere here and goes below. I like the width. I don't like the height. So let me show you guys another way, and this one's a little bit more freelance. You can kind of change the window however you like. I'm going to go to window this time, and I like how my x values are spread out. I don't like the height of my graph, so it's too tall. I only maybe want to go from, see, as you can see, we really only need to go from maybe +1 to -1, and we'll see most of the graph if we do that. So instead of letting my graph go from a y value from -10 to +10, I'm going to go down here, and I'm going to change it to -1 and +1, and that way it won't look so flat whenever we're graphing it. So now check out my graph. Now it looks a lot more friendly, a little bit more easy to look at. All right, so now here's the magic time. I want you guys to see if you can find this 0 here that is on the left. And by the way, before we go any further, if your graph still doesn't look like this, you might want to check your mode button and make sure you are in radians. You should be in radians, not degrees. If you're in radians, if you're in degrees, switch it back to radians. That's very important. You can actually fail your entire AP test by being in the wrong setting here. So make sure that you are always in radians in this class. We will never do degrees in here. It'll always be radians. All right, so anyway, back to this. Your graph should look like this at this point. Now I want you guys to go ahead and pause the video here, and I want you to see if you can find this 0 here. And when you unpause the video, you will see the keystrokes you should have pressed, as well as the answer for what that particular point where it touches the x-axis is. So you should have gotten -4.712 blah blah blah. Okay. Second, trace 2, scroll to the left, enter, scroll to the right, enter, enter. Okay? See if you can find the other root over here on the other side. Pause the video. When you unpause it, you'll see the solution. Well, it looks like I wasn't very creative. It's the same answer again. It's symmetrical. It's just an opposite sign. I promise it does not always turn out that way. So once again, second, trace 2. I had to scroll over here until I was close to the left of that root, and then I pushed enter, and then I scrolled a little more until I was to the right of the root, and then I pushed enter again, and then enter for the guess, and we get 4.712. All right, now I want you guys to pause the video and see if you guys can identify the intervals where f is increasing and the intervals where f is decreasing. So just as a quick picture, to the left of negative 4.712 and to the right of positive 4.712, my derivative is below the x-axis, which means my derivative is negative, which means that f is decreasing for the green zone. F would be increasing in the pink zone because that's my derivative. It's above the x-axis, which means it's greater than 0, which means my slope is positive, which means f is increasing. So this is how you would write your answer. Right. Now some of you guys might be looking at this thinking, what in the heck, Mr. Bailey? That's not what I got at all. And the reason why your answer is a little bit different is because you might have forgotten something. We only care about this interval. So let me take you back to our graph really quick and I'll explain it to you. All right. We're only going from 0 to 2 pi. So I do not care about anything to the left of 0. And then 2 pi probably stops. 2 pi is 2 times 3.14, right? Which is 6.28. So 6.28, we could probably scroll and find where that is approximately. Let's see if we can find where 6.28 is. Right about there. So the graph is going to stop right here. That's all we really care about is at that point. So the graph is increasing from 0 up to positive 4.712, and it's decreasing from 4.712 up to 2 pi. And that's why I had my answer recorded the way that I did on the last slide. All right, so this one was a little bit different because it had an interval. A little bit of a trick I threw in there. Watch out for that kind of stuff. All right, so here's one for you. I would encourage you guys to go ahead and try to do this one completely on your own from beginning to end. And when you unpause the video, you will see the solution. So to begin, here's the derivative that I've written up here at the top. And then here's what the graph looks like. But I don't like that graph. It's not high enough or low enough. And also, we don't need this much of an x-axis. We only need to go from 0 to pi, right? So I'm going to adjust my window. And if you guys want, you could have done the same thing. So I'm going to go to Window. I don't think my y values need to go much higher or lower, but I do know I want my x values to go from 0 up to just pi. Where's my pi button? There we go. And then as for the y values, I'm just going to I'm going to make it a little bit higher. Like let's say we're going to go from negative 15 to positive 15. Might still not be enough. All right, let's see what that looks like. So I changed my window. You know, I only wanted to go from 0 to pi on the x-axis because that's all we really care about. And also, I changed my y-axis so I can kind of see the entire curve. But there we have it. All right, so now based on this, I can now show you guys the rest of the solution. So the next thing we should have done at that point was you should have found the places where it touches the x-axis. There's 3 of them. It's 0.155, 1.202, and 2.249. Now that you know that, all the pink areas are the places where the derivative is above the x-axis, which means the derivative is greater than 0, which means that f is increasing on those intervals, which are from 0 to 0.155 and from 1.202 to 2.49. And then the green areas are all the places where the graph is below the x-axis, so that's between 0.155 and 1.202. So that would be your first interval. And the other interval would be from 2.49 up to the end, which our graph is supposed to stop at pi. So f is decreasing on those intervals because the derivative, the graph that we're looking at, is below the x-axis, which means that the derivative is negative, which means that the function, the original function, is decreasing on those intervals. So that is how you can be using a graphing calculator to answer those questions. Now, an additional thing, just for the fun of it, because it's fun, is I would challenge you guys to pause the video here and see if you can figure out what happens at this point on the original graph of f. Is that point a relative min or a max? How about here? And how about here? Determine if those 3 points are places where the graph of f has a relative min or a relative max. And when you unpause it, I'll show you the solution. Okay, so here at this point, the first one, we're going from left to, if we're going from left to right, we're going from a pink to a green, which means we're going from a positive slope to a negative slope, which means that that would be a max. Anytime your slope goes from positive to negative, that gives you a max. This one is going from negative to positive, which is the opposite. That's a minimum. And then this one is the same as the first one. It's a max. All right? You didn't have to answer that one, but just for a little extra thinking. All right, that does it for our lesson for the day, and we'll see you guys later.